acid-base neutralization. Remember that this is a double replacement reaction with a little bit more specificity. So what we have is a base, and what I've just got the OH negative labeled here because it doesn't really matter what the other part is. It's the OH negative that says that it's a base. And the hydrochloric acid, which I have listed as H+, because it's really just the H+ that matters to us. They're aqueous, which means that the positive and negative ions have separated in solution. They're just floating around being ions. And when they come together, they make water, which is a liquid because the two H's and the O bond. They're not floating around as H pluses and O negatives, so they aren't aqueous. They're actually bonded and not an ionic bond like these other ones that come apart in water. They are water. They're a covalent bond. So that's different, and that makes them a liquid rather than aqueous. Now the salt that gets formed by the metal and the non-metal that used to be attached to the H+ and the OH, that salt is aqueous. And the only way to make it into like the salt that you would recognize as a crystal form would be to evaporate the water off of it. And if you've ever seen salt on ocean water, wherever there's been an ocean water and then there's been evaporation, you'll see a little crust of salt there, and that's what that is. So those ions, in this case the Na+ and the Cl negative, are just sort of floating around, and until you take their water away, they're not actually bonded. So that makes them aqueous. They're their ionic forms, separate in solution. So back to the experiment, what I've got set up here is a column of water, and I've set it with a universal indicator. A universal indicator changes through the colors Roy G. Biv, going from an acid to a base. So you can see that in your equation I've underlined acid in red and underlined base in a dark blue. So green is neutral, it's in the middle. If I were to add one of these to it, it's going to shift either way. So I'm going to start with H+. Actually, nah, let's start with OH. And when I add the OH to this solution, it's just going to be, I'm adding the NaOH to water, which means that it's got more OH negative ions, which means that it's going to become basic. So we can expect to see, actually maybe let's just try this with the droppers for now. We can expect to see a little bit of a color change. And as you can see, the top of it is darker and the bottom is still like a light green. So I can just keep adding, and you can actually watch the base sinking through the solution because bases are heavier than water, and creating a change in the color as it goes. So the indicator is showing us that the base is descending through the water column, changing the pH from 7 down to, well, the strongest NaOH would be, pardon me, a pH of 14, which means that your hydrogen concentration, hydrogen ion concentration, is times 10 to the negative 14th, which means ridiculously small. It's basically non-existent at that point, because it's all been changed into water by the OH negative ions. Add a little bit more here just for some fun, get it completely changed over. All right. Now, we'll just speed up the mixing process a little bit here. Got a nice beautiful blue. I could probably continue trying to get that color darker, but you can see the shift from green to blue now, and so we're dealing with the base. Now what we want to do is introduce the acid. See the color shifting? Where the acid gets dropped in, it completely neutralizes the base and turns it into an acid, but as it falls down the water column, the base still has clout down at the bottom. Eventually, this whole thing is going to turn red. Now, acids are typically a little bit lighter than bases, so it takes it a little longer. I don't know if you can see the beautiful swirling pattern in that, but it's quite lovely. You can see that there's a little bit of green still remaining, but the swirls of acid going through and neutralizing, so all the H plus ions are attaching to the OH negative ions and creating water, which is neutral, and if there's any H plus ions left over, that's when we get the fact that it's acidic. So spin it up there, very pretty. Now, in an acid-base neutralization, you've seen a base, you've seen an acid. In the neutralization, it goes back to salt and water, which means that it should return to its original green color. I think that the base and the acid that I've chosen, I think the base is a little bit weaker. So I'm just going to dump some of this in here. Got to be careful with this one because we have to reach the exact moment at which they are balanced, and there's no leftover H pluses or OH negatives, because that would not be a neutralization. They're supposed to neutralize each other. If we overshoot, I guess we can just add some more acid. Looks like we're still on the acidic side of things. If you guys were here, I'd be telling you to tell me when to stop. But I'll just have to try to manage it on my own. Still going. So you can see that the pH has changed. It's no longer red, so it's a weaker pH now, getting closer to 7. I believe it's about a 3 when it's that color. Remember that the pH goes the other way when it's an acid, so when we were looking at the red, that would have been a pH of 1. And that would have told us that the hydrogen ion concentration was actually times 10 to the negative 1, which is 0.1, 10%, actually pretty high, considering that there's a bunch of other stuff in there, like water. We're getting close. Now you can see even the bottom part has a little bit of a green tinge to it, and we're really getting close to that neutralization part. Sorry about the jingly noise. One more? One more. We'll call that one good. We got a lot of green in there, so our pH is going to be pretty close to 7, which means we've got an acid-base neutralization. The acid and the base have given up their ions of H plus and OH. Those have bonded together to make water, and the Na and Cl are just floating around in there and doing nothing because they're just a salt. A salt is an ionic compound that is not an acid or a base. So it's kind of self-defining